from Lebanese American University. At least now I can read that. Yes, and Gada will tell us about free boundary problems for modeling of atherosclerosis. Please, Gada, you can start.
Thank you, Vitali. So, as Vitali told you, my name is Gada Abi Yunes, and I am a PhD student at the University Klod Bernar Lyon 1 under the supervision of Professors Vitali Volpert and Nader El Khatib. First, I just want to take a moment to thank the organizing committee for this opportunity to participate to this seminar. And today I am going to talk about a free boundary problem in the mathematical modeling of atherosclerosis. So this presentation outlines the following points. First, we are going to start with a quick overview on the plaque growth in biology. Then we move to the mathematical part. We start by proposing a mathematical model. Then we are going to simplify this model to prove the existence of solution for this model. And then we are going to deal with traveling wave solutions. And finally, I'm going to do a very brief summary on how to find a solution for free boundary problems for reaction diffusion systems, I mean in general form in 1D. So let us start. So here in the slide, what you can see, we have a longitudinal section of an artery. Of course, we can see here the arterial layers, which are layers of the arterial wall. And you can see here the lumen where the blood circulates. We are in fact interested in the first layer of the arterial wall called the intima, and this barrier that separates this layer from the blood flow, which is called the endothelium. So as you may know, atherosclerosis is an inflammatory disease characterized by the penetration of LDL particles and white blood cells to the intima. So these white blood cells, we call them monocytes, and when they reach the intima, they differentiate into macrophages. So since LDL is a dangerous substance, macrophages try to phagocyte the LDL or to engulf the LDL particles, but unfortunately they cannot destroy it completely. So they release cytokines to promote the recruitment of new macrophages. But in releasing these cytokines, this allows penetration of new LDL particles. And here we have a positive feedback situation, which this makes atherosclerosis to be a chronic inflammatory disease. So when macrophages engulf LDL particles, they become engorged with lipids. We call them foam cells. Foam cells undergo apoptosis, or they die, and form an atherosclerotic plaque. This is what you can see here in yellow. Of course, this plaque hardens over time and it narrows the blood flow. Here you can see clearly that the plaque changes the geometry of the arterial wall, and we can imagine this motion of this layer, which is the endothelium, that grows in this direction, And here we had the inspiration to work with a free boundary model that I'm going to talk about in the next slide. And notice that if we consider this boundary here, or this layer here, it is moving with time. In fact, it is going to be the moving boundary in our domain. I will explain this right now. In this diagram, it is a reproduction of the figure that I showed you before. Here are the arterial layers. This is the first layer, the intima, and this is the endothelium. And here is the lumen, where the blood passes. So of course, here the particles come from the lumen and accumulate here and cause this this endothelium, this barrier here, to move to in this direction. So we take our interval to be this red line. We are going to work with a 1D model. So we take x going from 0 till L of t. Of course, this boundary L of t depends on t because it is going to move with time. It changes with time. So this is why the boundary is a function of time, and L of t, in fact, is the size of the domain. So we propose this mathematical model. Here we have three equations. The first two equations are partial differential equations of reaction diffusion type. In these equations, we model the evolution in time of the concentration of M that refers to the macrophages, A that refers to the cytokines, to the concentration of cytokines, and F that denotes the concentration of foam cells. In the first two equations, the first right-hand side terms are for the diffusion of macrophages and cytokines, respectively. In equations also 1 and 2, the last two terms are for the reaction part. Let me explain this term one by one. This term, del M multiplying M0 minus M, it refers to the proliferation of macrophages. And here M0 is the concentration of the physiological equilibrium value of macrophages. This term, D1M, is for the degradation of macrophages. Here also we have this term, it refers to the production of cytokines due to the presence of macrophages and to cytokines themselves. And here we have in the denominator an inhibitor term. In fact, this denotes a mechanical saturation due to the fibrous cap formation. And this term denotes the degradation of cytokines. And finally, this lambda M is for the differentiation of macrophages into foam cells. Now for the boundary condition, here also I put the interval to understand better. For x equals 0, there are no fluxes, so del M over del x and del A over del x are 0. While on the other boundary, when x equal L of t, we express the flux of M through this boundary by a function of A, because M and the macrophages or monocytes enter the intima due to the presence of A. And here also we have in the denominator this term, in fact, refers to the anti-inflammatory cytokines, which inhibit the product or the activity of pro-inflammatory cytokines. So it is an inhibition term. And of course, there is no flux for A for x equal L of t. Now, how to model the size of the interval? We start by expressing L ec of t. So EQ for equilibrium. I will explain this in the next equation. Here we start with an initial size L0. And then we express the motion of L ec of t by the presence of macrophages and foam cells within the intima. Let me notice something. In this model, the motion of the boundary is due to the flux of macrophages through the boundary, as well as for their interaction within the intima. So if you consider the endothelium, I recall it is the barrier that separates the arterial walls from the lumen. If we consider it as a linear elastic medium, then the force needed to extend this endothelium is given by Hooke's law. So this is the force, and this is, here we apply the Hooke's law. Here we have a constant K, and this is the displacement. So here is L equilibrium minus L of T. But in our case, here also we consider the pressure of the blood flow. It is an external force. We have that this force F equal to P. So for simplicity, in this model, we are going to take P to be 0. When we take this assumption, L of T, the size of the domain, turns to be L0, the initial size of the domain, plus the integral from 0 till L of T of a constant times the concentration of macrophages, plus a constant times the concentration of foam cells. In other terms, it is the presence of macrophages and foam cells in the intima, which leads to the motion of the boundary, which causes this motion. Now, in this first step, we are going to do some simplifications, but later on, I will talk about more general models without doing all the simplification. So keep in mind that here first, we reduce our system from 3 equations into 2. So here, we remove the equation for A. Just for simplicity, we consider that the diffusion term for the cytokines can be neglected and that the concentration of cytokines remains constant with time. So del A over del T is 0. And we express A through M. So we get the following. So this is the equation for M. It remains as it is. Also for the equation of F, for the equation of L. Now for the boundary condition, before the flux of M at the boundary x equal L of T was a function of A, but now it is a function of M. This is just for simplifying. So again, here we have this simplified model, but what I'm going to do is to take a more generic model. So, for instance, we have here M and F. I am going to take instead of them U and V. The reaction part, instead of taking several terms, I am going to express all this through a function G of U. So here also the production of foam cells is also expressed as small gf of U, and so on. And the boundary condition, instead of this function, I'm going to take a more general one, which is H of U. Let us go back to the expression or to the form of the size of the interval L of T. So here we have this equation 11 that I just explained. We would like to retrieve L prime of T, so we differentiate and we get this form for L prime of T. Also here we are going to take another assumption. So here we have the first assumption we took, we removed A from the system, the equation of A. And here we are going to take assumptions on L prime of T. So keep in mind these two assumptions because we are going to talk about a more general form where we do not consider these assumptions. So to simplify, as you may notice here in the numerator, we have this term under the integral. So we took K2 equal to K1, and we took F of U is 0. So this term is cancelled, it is 0. And we take K1U at L of t, and K2 plus K2V at L of t, very small, positive, very close to 0. In other terms, the denominator can be estimated by 1. And finally, as an estimation for L prime of t, or as a form of L prime of t, we keep only this term in the numerator. So we have equation 13. Now we have a simplified model with a free boundary. What we are going to do is the following. We are going to do a change of variable, which is the following: y equal x over L of t. And this change of variable allows us to transform this simple model with free boundary to a model with fixed boundary. And instead of small u and small v, you are going to have big U and big V. The new model, after the change of variable, becomes the following. And here I recall that it is a model with fixed boundary. Instead of x, we have y, and y runs from 0 till 1. This model is expressed here. I am going to talk of some particularities of this model. So, after the change of variable, it is a model with fixed boundary. However, when we did this change of variable, we got coefficients that are space and time dependent. Moreover, we have these functions that are highlighted in yellow. These functions are non-linear. So, our goal is to find a solution for this problem, which is problem 15. But we have non-linear terms. We are going to do the following. We will introduce new functions n and v that we are going to put instead of L and U. And this way, these non-linear terms become linear terms. This is the system, but what we are going to do here is to remove the equation for L prime, and now we will be finding the solution for the system without the equation of L prime. Of course, it is system 17, because I'm gonna recall this in the coming slides. So again, here we have linear terms and we have coefficients that are time and space dependent. Okay, I will do a small summary to show you how we are going to proceed. Again, we had a free boundary model. We did a change of variable. So we retrieved a fixed boundary model with space and time dependent coefficients and nonlinear terms. We introduced the functions n and v. And now we got a fixed boundary model with linear terms, but it has space and time dependent coefficients. So we will be studying the solution for this model, and then by applying the fixed point theorem, we can find we can prove the existence of solution for this fixed boundary model with nonlinear term, and then we deduce the existence of solution for this free boundary model. Before I proceed, I need to recall a definition on Holder spaces. So by the definition, HL of omega bar. First of all, L is a non-integer term. So it can be a fraction, it can be, for instance, 2.5 or any given non-integer number. So HL is a Banach space. In this space, all elements okay, it is a set of functions. So let us call this function u of x. U of x is continuous. Moreover, the derivatives up to order the whole part of L are also continuous, and the derivative of order the whole part of L verifies Holder condition with exponent L minus whole part of L. So we have the semi-norm, it is a semi-norm, is finite. To prove the existence of solution of system 17, first of all, we fix L to be between 0 and half. We have several conditions. If these conditions are satisfied, then we can say that this problem 17 has a unique solution in this Holder space L plus 2, L over 2 plus 1. So for the notation here, we have here two numbers because u is a function of x and t. Moreover, we can find an estimate for the norm of u in the Holder space L plus 2. I will talk very briefly about the proof of the theorem. To prove the theorem, we have to define this operator. So these terms appear in the equation of u and the following functions. So this is g, h, where we can see v, the function that we have introduced. And this function here also, where we can see the terms that appear in the boundary condition. Using the conditions of the theorem, we can prove that the coefficient of the operator L belongs to this Holder space, and also we can prove that B1, F, and phi belong to these Holder spaces, and moreover, one can prove that F and phi satisfy the compatibility condition. In our case, it means that the boundary condition at time t is equal to the initial condition, which is in our case 0. So, how can we prove the theorem? In fact, we relied on a theorem in the book entitled Linear and Quasi-Linear Equations of Parabolic Type. In this theorem, there are several conditions to verify, and these are the conditions. And since we can verify all these conditions, we can prove the existence of a unique solution U for the system 17. Moreover, we can find an estimate for this norm of U using the norms of H, G, and V. If you remember, I told you that we are dealing now with a system where there is the equation of U with boundary condition and initial condition without the equation of L. Now let us go back to the equation of L prime. L prime has this form. So we retrieve L of t by integrating, and we need to know to which space belong L. In fact, according to the theorem, H is of class C1 and V is of class H L plus 1 over 2. So we deduce that L belongs to the Holder space H of order L plus 3 over 2. So why do we need to know the space of L? Because we want to define an operator. This operator maps N and V to L minus L at 0 and U. So these terms N and V were introduced to remove the nonlinear terms, This operator maps the pair NV to L minus L0 and U. N and V belong to spaces of order less than the order of spaces of L of T and U. I will explain. Let us consider N of T is in Holder space H alpha and L of T is in Holder space H beta. Beta is greater than alpha. And similarly, the space of U is of order greater than the order of the space of V. And here, in the example I gave you, beta is greater than alpha, then there is a property that states that H alpha is included in H beta is included in H alpha. I will talk about this in a couple of minutes. Under the conditions of theorem 1, the operator A is bounded and compact. So it is very straightforward here to prove that the set A is bounded, because if we take N and V in a bounded set, their image, which are L minus L0 and U, have bounded norms. So first, for U, we use the estimate that we got from the theorem. And also for L minus L0, we can do the estimate, and clearly we can say that the norm is bounded. So for the boundedness, it is straightforward. Now, for the compactness, as I told you, the spaces to which belong L and U are of order greater than the spaces to which belong N and V. So here we talk about the compact embedding. I will go back. Is there any question? Someone wants to talk?
No, I don't think. No, there are no questions. Continue, please.
Okay. Well, I was talking about the compact embedding. I will go back to the example of H alpha and H beta. I told you for beta greater than alpha, H beta is included in H alpha, and there is a compact embedding from H beta to H alpha. In other terms, every bounded set in H beta is compact in H alpha. So for the construction here of A, we take the same sets. So A goes from these sets into themselves. However, the sets of L and U are subsets of this set. So here we use the compact embedding to say that the image of any bounded set is compact in the sets to which L and U belong. I don't know if it is clear. If you want to interrupt me, please do not hesitate.
No, Gada, don't worry. It's very, very clear. So please continue. We'll discuss it later.
Okay. So under the condition of theorem 1, we can also say that the operator A admits a fixed point. So I will explain how to prove this proposition, and then I will explain why do we need this proposition. To prove this proposition, we are going to partition our interval, our time interval from 0 to t to different sub-intervals. I will start with the first sub-interval 0t1, and I will tell you how we proceed for the other sub-intervals. In this sub-interval 0t1, we already know that the initial condition is for u at y0 is equal to 0. It is taken from the beginning. In this subinterval, we can apply the theorem because the initial condition is 0. So we can prove that there exists a solution u1 star for system 17 over the interval 0 t1. And for a particular choice of t1, we can deduce that the operator A defined over the interval 0 t1 has a fixed point. And in the next slide, I will show how we can find this. So, for now, we have a solution for system 17 over the interval 0 t1. Let us move to the interval t1, t2. At t1, the solution is u1 star at t1, but it is not 0. So, in order to apply the theorem over the interval t1, t2, we need to do a change of variable. We take, instead of u, we take mu, that is the difference of u minus this solution here, u1 star. And this way, the new variable has a 0 initial condition. This mu at time t1 is equal to 0. So, in this case, we can apply the theorem and find a solution u2 star over t1, t2. And for a particular choice of t2, we can prove that the operator A defined over t1, t2 has a fixed point, and so on. And finally, by the semigroup property, we can prove that we can find a solution over 0 t1 such that we can define it as a piecewise function. Over 0 t1 it is u1 star, over t1 t2 it is u2 star, and so on. So maybe one may ask why we cannot directly find the solution over 0 t. The answer is because in our estimation, we are going to have T1 appear, or the time appears. So our goal is to prove that the unit ball is strictly mapped into itself to prove that we have a fixed point for the operator A. So if we take the unit ball, N and V in the unit ball, we need to prove that the norm of U and L in the holder spaces are less than 1 strictly. So the method here is a little bit complicated, but I am going to explain it in a brief way so that you can understand it. So we have the following. From the estimations that we got, we have that the norm of U 0 is less than M1 T1. So if we take the T1, so here I took the example for the interval 0 T1. If T1 is small enough, we can say that this norm converges to 0. And similarly for L minus L at 0, it is less than a constant times T1. And if T1 is close to 0, then it converges in C. So if we take any order for the holder space which is less than the holder space order of L and U. So for instance here, this is the order for the space, holder space of L. This is the order for the holder space of U. If we take gamma 1 and gamma 2 that are less than these orders, Then we can say the following. I will talk now only about L, and this applies to U. We know that L1, so L minus L0 converges to 0 in C, and it is bounded in H L plus 3 over 2. It is bounded because I showed earlier that we can find a bound for the norm of L in this space. Then we can deduce that any intermediate norm between the norm of H L plus 3 over 2 and the norm C converges to 0, and this applies for H gamma 1. We can say the same for U, and this way, by choosing small t1, we can prove that the image of N and V, which are in the unit ball, is strictly less than 1, and this way we can prove that the operator A has a fixed point. I recall we had a model with nonlinear terms. The nonlinear terms are highlighted in yellow. We introduced the new functions N and V. We had this model with linear terms. Then we had this operator NV that maps for NV L minus L0U. It has a fixed point. What does it mean? We already find a solution for the first equation with the boundary condition and initial condition in this model. We have a solution U. If we take this solution U and we fix NV, we have that A has a fixed point. So we take this fixed point to be U and L in this model. So we can prove that this model has a solution. Now I am going to talk briefly about traveling wave solutions. Of course, here we take this first equation. It is the equation of U, a partial differential equation of reaction diffusion type. And we took also this form for L prime, where L is the size of the domain. Also here we have this boundary condition, but in our case now, for the traveling wave solution, we take x between minus infinity and L of t. So we look for solution of this form U, x, and t is W of x minus ct, where c is the velocity of the propagation of the solution. So if we express x minus ct to be zeta, then we have W verifies equations, this one, and for C, we can find C from the boundary condition. For more simplification, to write this model with two first-order equations, we take P to be W prime, and we have these equations in 21. So here we did the following. We found in this lower panel, here we have W and P of W. In this lower panel, we have H at W0, and we plot P of W for different velocities. Here W0 comes from the boundary condition. The velocity that verifies this equation, which is in 20, in fact comes from the interaction of P of W and H of W when they intersect. I said interaction, sorry, it is the intersection. When they intersect, this is W at 0. So this is a graphical way to find how we can plot these solutions and how we can verify the boundary condition. Here also, I'd like to show you how we can find graphically the solution for system 17. If you remember, the system, no, sorry, here it is not system 17, it is the system with free boundary. You can see that the solution, it propagates with the space. So because the space, it increases with time, we can see that with time the solution takes values for how to say, for greater values of x, and we can see that here we have a steady wave. You can see the waves here and with a specific upper value. And finally, here I show you some of the results, just to say very briefly, when we change some parameters, we notice that the parameters that refer to the production and accumulation of macrophages, when we increase them, this means the plaque, the size of the plaque increases with a higher velocity. And just 2 minutes to talk about a free boundary problem for reaction diffusion systems of general form. As you remember, I told you there are assumptions that we took earlier to simplify the model, but in fact we could prove the existence of solution of a free boundary problem of reaction diffusion of general form. What I mean by this is, if you look at the equation 22, U is a vector and F is a vector. Also, in the boundary condition in equation 23, H is a vector. So we can prove in a similar manner, we use the same construction of the proof, that there exists a unique solution for this problem, and also we can find an estimate for the solution. And thank you for your attention.
Okay, thank you, Gada. It was not easy to present these complex mathematical results. So, well, we'll discuss a little bit. So first of all, the main result you present here is the proof of the existence of solutions. When you present it in the mathematical audience, it's kind of a classical question, existence of solution. Everybody proves existence of solutions. Nobody asks why we prove existence of solutions. However, if you do it in a more general audience, like for example, then it depends. If these are biologists, because this work is somehow related to biology, well, usually biologists, they just don't understand, but they don't ask questions, and they take it, okay, there are these crazy mathematicians, they do something, nobody understands what they do, and it's okay. However, if you present this in the physical audience, okay, the reaction is different, because, I mean, theoretical physicists, they understand quite well mathematics. And their reaction usually is, okay, there's no need to prove existence of solutions. We know that the solution exists. All that is nonsense. You just waste your time. So, I will not, well, I can ask you the question, why do you prove existence of solutions? But I don't expect you to give an answer, but I want you to think about this question. Because there are people who spend all their lives proving existence of solutions. You become a huge world expert in the existence of solution of some very complex problem. But sometimes we should ask the question why we do that. Maybe we should not do that. Maybe it's obvious, or maybe it's not obvious, but it's no interest in that. So this is what I suggest for all people who are still listening us to think about. When we do something, let's try to understand why and what for we do that. Well, a partial answer to this question is that, okay, if we prove the proof of existence of solutions usually shows that the problem is well posed, mathematically well posed. But if the problem is mathematically well posed, rather often this means that it is physically well posed, that the assumptions of the model are consistent, they're physically correct, there is no some like mistakes in the formulation of the model. Well, it's quite abstract idea. Well, then, but still, I think it's a quite serious argument to prove the existence of solution. Another possible way to think about that is that when you prove the existence of solution, you impose some conditions. In particular, one of the conditions was kind of, please return to some, I don't remember which slide is that, but somewhere in the beginning where you have this formula for L prime. Just complex formula, L prime equals some. Yeah, this one, yeah. Very good. This equation 12. Beautiful formula. Then you say, okay, let us suppose that the integral is 0. Let us suppose that the denominator is 1. And we obtain L prime equals h of u, formula 13. In particular, you suppose here that the k1 and k2 are very small, so the denominator is close to 1. If you don't do this assumption, so a priori, you don't know whether the denominator remains positive, or even if it is positive, you need some uniform estimates. So this is an important condition. You didn't pay too much attention to it. So if somehow something happens, well, we can imagine that the solution, well, mathematically they say explode, not physical explosion, but the solution either becomes unbounded or does not belong to some function spaces, loses some properties. So this is important. So we impose some conditions, then the solution exists. This means that if these conditions are not satisfied, we don't know, but maybe solution does not exist. And if the solution does not exist, so this becomes more like more complex. So what do you think from your experience of this problem? Is it possible that under some conditions, this solution does not exist for all times and either loses its regularity or becomes unbounded or something else happens? It's a question for you.
Yes, in fact, I noticed this in the numerical simulations for some values of K1 and K2. The solution explodes and there was a huge jump. The problem was that this term goes to 1 and then the denominator becomes 0. So it didn't work, at least graphically. I can assume.
Yes, so please, this is important for presentations like that and for your understanding. So the solution, we don't know, but it is possible that the solution does not exist under some conditions. So in this case, the proof of existence of solutions makes more sense because not always the solution exists. Okay. Yes. And also another point, these are, as you say, numerical simulations. When you do numerical simulations, the properties of these numerical solutions somehow are related to the property of this problem. If the problem is well posed, if you prove the existence of solution, if the solution is bounded and belongs to some function spaces, it's not what I say, it's not a mathematical theorem, but somehow it implies that your numerical solution will also behave in some good way.
Yes.
You see? So this is important. So all that arguments which are maybe not very precise, but they show that sometimes it might be useful to prove existence of solutions, even if it is a pure mathematical work with very complex developments, formulas, spaces, and so on and so forth. So keep this please in mind, because when you will present it somewhere, well, somebody can ask you a question, but why do you do it? It's so, it takes you like so much time, it's so difficult, but why to prove the existence of solution? So you should be able to explain that, though it's not very easy to explain. Okay, these are some general considerations. Then some more like specific points. A very small point, it's slide 13, please open that.
Just
The next one, yes, 13.
I cannot see my slides.
You don't see, it's for me, it's 12. So it's the next one, if you can. And what happens with your slides?
They disappeared from my
They
screen.
disappeared, okay.
Okay, now, okay. I will move now to 13. Can you see slide 13?
No, maybe, yeah, it's 13, but then I'm wrong. It's not 13. No, sorry, 19. In fact, 19, never mind. Okay, if it works, then open 19, okay. Yeah, I like that. By theorem 5.3 of the book, Linear and Quasi-Linear Equations of Parabolic Time. I understand what is the problem. You just cannot pronounce the name Ladizhenskaya. This is why you don't you don't say that. But in fact, you should at least give a reference, because of course it is a famous book, but maybe not everybody knows the authors of the book. So it's Ladizhenskaya, Salonikov, Araltseva, indeed linear and quasi-linear equations of parabolic time. It's a classical book on parabolic equations, quite old. I think the first edition was published in the 60s, 67 or something like that. Now maybe not so many people use it because it's a quite complex reading, but I still think that it is a very useful book with many very useful results, but it's really not an easy reading. But now with all your experience in that, I think that you can appreciate and really agree with me that it is a useful book. So the reference is Ladizhenskaya, Salonikov, Araltseva. By the way, they have also another book on elliptic equations without Salonikov, just Ladizhenskaya, Araltseva about elliptic equation. Also a very good book, but we did not use it in this book. Okay, the next point is about fixed point theorems. You mentioned it kind of like not paying too much attention to that. Okay, it's another classical mathematical result. But I would suggest you, when you do presentation like that, to recall what is fixed point theorem, and to say in particular that maybe there are different formulations of fixed point theorem. In particular, what you use in this work, it is called Schauder fixed point theorem. So it is better to give formulation of the theorem and condition of the theorem. In particular, it says that if you have a nonlinear map which maps some set inside itself, and if this map is compact, then there is a fixed point of this map. This is a classical mathematical theorem. It's a kind of a basis of functional analysis, of nonlinear analysis, but still it can be useful to recall it from time to time.
Yeah.
Okay, so the next, well, in fact, there are only two remaining questions in in my list. I think I'm sure that our listeners are tired and some of them left, but still I will continue. So please return to the same formula for L of L prime, and L. So this is in fact what is the most important, one of the important points of this work. You mentioned that, but I would like to repeat. In particular, Anastasiya is still listening to us and some other people. I would like to discuss a little bit this question. These three equations, 11, 12, and 13. We start with the equation 11. 12 is kind of intermediate. 13 is what we obtain. 13 is tells us that the speed of the moving boundary is determined by the flux through the boundary, because h, it's exactly, if you return to the formulation of the problem, it's exactly the flux through the boundary. So what we obtain? So in this equation 13 tells us that the boundary moves because of the cells intersecting the boundary, coming through the boundary to the domain. Physically, this is very clear, right? There are cells crossing the boundary, and this is why our domain becomes larger. And this what people usually consider in all free boundary problems. In biology, in physics, in chemistry. So there is a flux through the boundary, and this flux through the boundary determines the motion of the boundary. Maybe you have heard about what is called Stefan problem, things like that. All is based on this assumption. But when we study biological problems, we say that this may be not true in biological problems. This is the main point. This was the starting point of all that. This may not be true because biology is different from physics. Why this may not be true? Because cells, inside cells penetrate through the boundary, it's okay. But then what happens with the cells? They can divide or they can die and disappear because there is no conservation of mass. This is the point. Where all these free boundary problems comes from the conservation of mass and from the conservation of energy. Like, for example, melting problems, like in physics of metals, melting problems, huge amount of like works. It's an absolutely classical, very important subject. All these problems are based on mass conservation and energy conservation. This is why this boundary moves. Biology is different. There is no mass conservation. It depends on the formulation, of course. What means no mass conservation? It means that we don't take into account nutrients, for example, which are there inside. Cells consume these nutrients and they begin to divide. So, or they die and they are removed by neutrophils or other cells. From this point of view, there is no mass conservation. So, the boundary can move not only because of the influx of cells, but because of the processes which take place inside the domain. This is why we consider this equation 11, which tells us that the width of the domain is determined by the number of cells inside. Not by the flux, but the number of cells, by the number of cells inside. This is the main assumption of this. Anastasiya, do you understand my explanation?
Yes, and now I become
what?
Understand
what?
Something. Yes,
what?
I understand, and I have a question for this. But you say that there is no mass conservation in this sense for the biology problem, but here you obtain that we have the same equation for the moving boundary as it is in the physical tasks.
You mean equation 13?
Yes.
Okay, this is where I'm coming. So we start with the assumption that, okay, cells can divide, for example, or die, and this can change our this can move our boundary. Then we do some simplifying assumptions, and we come exactly to what we say doesn't hold. And then we work with this. Yes, this is true, because we need to start somewhere. And this is exactly what I wanted to point out, that we reduced our problem to a more classical case. We studied it. It was quite complex development. We proved the existence of solutions. Then, and this is what Gada did not say, that the next step was to prove to consider the problem without these assumptions, without these simplifications. In fact, it was a problem 11. So it was the next step. Is it true, Gada? I think you did it, right? In the next work. Yes, you did. Okay, so in fact, yes, we can do that in this more general case without these simplifications. This is exactly where I was going to come. Right. My last.
One more time.
Yeah, go ahead.
What you can do is a more complex case of the equation 11. The same proof of the existence of the solution.
Yes, yes. Gada, you can answer if you can. You answer.
Yes. Look, Anastasia, I will go to the last slide. Here I showed you the problem, the more general form of the problem. Starting from this L of t, in fact, here f of u is not linear as taken in the previous form, okay, for the atherosclerotic model. So here f can be something other than constant u1 plus constant times u2 and so on. This is first. Second, we did the same method. So I will go to this slide for equations 13 and 14 and 11. So we went through this step, okay, and we didn't do any assumption. But the main difference was here. Look here, when we were taking this operator to map NV into L of t and u, okay, here is a definition of L of t taken is a function of v. So in the more complete model, the more general model, it is a function of v and n, but we follow the same steps.
Well, to make it short, 20 pages of some calculations, which I don't understand anymore.
And I think it would be useful if you formulate, I don't know, maybe restrictions for the coefficients of the biological problems where we can use the assumption of the boundary of the moving boundary depending on the cell influx, and when this moving boundary is governed by more complex case like equation 11. From the practice point of view, I think would be useful.
Yes, but I have to say something that when we take the more general form for L of t, there are additional conditions to take into consideration in order to ensure that we have a solution.
Okay, good. I have one last question. Return, please, to the model in the very beginning. Yeah, yeah, this one. Yeah. Well, listening to you, I was just thought that this. You say you explained that M0 here is a physiological value of this of the concentration of macrophages. But what means physiological value? This should be explained, because if you take a normal tissue, indeed there are resident macrophages, and we can say about the normal physiological value. However, here we consider aterosclerosis, and these are not, or maybe not only resident macrophages, but the macrophages coming from outside. So in this case, what is this normal physiological value if this is not normal physiological situation?
In fact, it is. So let me explain it in a mathematical point of view. So here we should have an upper bound for the concentration of M that we cannot exceed. And this is why we got the idea to impose a term to refer to this equilibrium that we cannot exceed. We don't want to have negative values here.
Now, of course, well, not negative values, but, well, rather bound. You want to have some bound. Yes, I understand that. But talking about biology, so, okay, then you don't say that it is normal physiological value, but you say that this is some upper bound of this concentration or something like that. Another way also to think about that is to suppose that M0 can depend on A.
Oh, okay.
Here it's a constant, but it can depend, and in this case it is, well, biologically more clear, right? You have this inflammatory cytokines, and you can say that if there is some concentration determined by this inflammatory cytokines. But okay. Okay, I don't have other comments. I think we had a good discussion. So Anastasia is smiling. It's good. So if there are no other questions, then we stop for today. I'd like to recall that the next time in 1 week, I think it's myself, right, Anastasia? I will give a talk. I don't remember whether I gave you the title or not.
Yes, you give.
So what was the title? Tell me.
1 moment. We have this information on our site.
Yeah.
On 13 October, Professor Wolpert with the talk epidemiological models with distributed parameters.
Oh, really? I completely forgot about that, and I was going to talk about something different. Okay, now it's
okay. We can change the title.
Yeah.
Now.
Okay.
If you would like to tell about something else.
Well, in fact, because I need to finish some work, and my idea was to finish the work and at the same time to prepare this presentation. And in fact, I was going to talk about lung obstruction during the coronavirus disease. So what we know is that, well, it's one of the serious clinical consequences that there are difficulties of respiration during this respiratory viral infections, right? So I was going to explain where it comes from, how to model that. Is it good? Is it okay? Is it okay as topic of Gada?
Yes.
You agree with that? Because I think that once in some lecture or seminar I mentioned that, but I don't remember exactly, and this work is not finished, so I'm planning to finish it and to explain it in more detail. So let's do that. So how to call it? Mathematical modeling of lung obstruction during respiratory viral infections. And I think that I will do it probably in English because I want to invite some of graduate students in particular who is present here. Yes, because not everybody still speaks Russian and even French, so then probably we need to do it in English, right? Okay, if there are no other questions, then thanks to the speaker, to the organizers, and to the listeners. We stop for today, and I will see you next week. Bye.
Thank you.
Thank you. Goodbye.
Bye.
Anastasia.
Thank you.
Thank you.
Anastasia,
Yes.
can you send us the link for next week's seminar?
Yes.
It is the
I will
same?
send. I will double it in the full email, and I resend the invitation link to your. Goodbye. Thank you for today.
Bye. Thank you.
Bye. Thank you, Anastasia.
Bye. Thank you.